Hello and welcome to the Drift to the Stars. I'm so glad you're here tonight. Perhaps it's been a long day, or perhaps you simply like to fall asleep with your mind somewhere vast and quiet, somewhere among the stars. Either way, this journey is for you. There's nothing you need to do right now, nowhere to be, nothing to remember. Just let your body settle, your breath slow, and your thoughts begin to drift. Because tonight, we're going to move gently through the universe itself. Not just one corner of it, but the whole extraordinary thing. Black holes and ancient light, dark matter and distant galaxies, the first moments of time and the long quiet that may follow. Some of what you hear may surprise you. Some of it may stay with you like a half-formed thought at the edge of sleep. And if these slow, calm explorations help you rest, please consider liking and subscribing. It helps others find their way here too. Now, if you're ready, let's begin. The universe is waiting, and it has been for quite some time. The universe is generally believed to be about 8 billion years old. This figure comes from careful measurements of the cosmic microwave background, the faint afterglow of the Big Bang, combined with observations of how rapidly space is expanding. It is one of the most precisely calculated numbers in all of science. And yet, not everyone agrees. Some observations of very ancient stars and early galaxies suggest they may be older than this estimate allows. Other researchers question the assumed rate of expansion or propose that dark energy, the mysterious force driving the universe apart, may have shifted over time in ways we haven't fully accounted for. These tensions haven't been resolved. Most astronomers still accept the 8 billion year figure, but the questions remain open. Could the universe be older than we think? Did something fundamental slip through our calculations? It's possible that what we call the beginning was simply one chapter in a longer, stranger story, one whose earlier pages we have not yet learned to read. Not every planet has a star. Some travel alone, completely unbound, drifting silently through the galaxy with no sun to warm them, no light to mark the passing of time on their surfaces. These are rogue planets, and they are far more numerous than you might expect. Most likely formed the way ordinary planets do, within a solar system. But gravitational chaos, the pushing and pulling of neighboring planets and passing stars, can eject a world entirely from its orbit, sending it out into the dark. Others may have condensed directly from gas clouds, like stars that never quite ignited. Because they emit no light of their own, rogue planets are nearly invisible. We can only detect them when they drift in front of a background star or glow faintly in infrared wavelengths. Even so, astronomers estimate there may be billions of them wandering the Milky Way alone, perhaps more than the number of stars themselves. Each one is a silent world. No sunrises, no sunsets, just the slow spin of a cold surface beneath an endless field of distant stars. The standard picture of cosmology describes a universe born in a single extraordinary moment, the Big Bang, expanding outward and continuing to do so, perhaps forever. It is a story with a clear beginning and a long, slow, open ending. But some theories imagine something different. A universe that does not simply expand into stillness, but instead reaches a turning point and rebounds. In these cyclic models, the cosmos collapses inward after an unimaginable span of time, then bounces outward again in a new expansion, a new beginning built from the remains of the old. Each cycle might erase the structures of the previous era while preserving faint traces, subtle imprints carried forward into the next universe like memories half forgotten. In this view, there is no true beginning and no true end. Only a rhythm, vast and patient, stretching across scales of time so large they lose all meaning to a human mind. The universe in this telling does not die. It simply starts again. For the first 380,000 years after the Big Bang, the universe was opaque. Matter and energy were packed together so tightly, so hotly, that light could not travel more than a short distance before scattering off free electrons. The cosmos glowed, but nothing could see through it. Then something changed. As space expanded and temperatures dropped, electrons and atomic nuclei slowed enough to combine into neutral atoms. In what must have been an extraordinary transition, the fog lifted. Light was suddenly free to travel. And travel it did. Those photons, released in that moment of first transparency, have been moving through space ever since. For more than 13 billion years. Stretched by the expansion of the universe from visible light into long, cool microwaves. We detect them today as the cosmic microwave background, a faint, nearly uniform glow arriving from every direction at once. It is the oldest light in the observable universe. Not from any star or galaxy, but from the universe itself at the moment it first became clear enough to be seen. In most solar systems, the balance of elements follows a familiar pattern. But in some corners of the universe, the chemistry is very different. When a planet forms in an environment rich in carbon relative to oxygen, and when pressures deep within that world are high enough, something remarkable becomes possible. A diamond planet. Astronomers have identified at least one strong candidate, a dense world orbiting a pulsar, the remnant of a collapsed star. Based on its mass, its size, and its likely composition, the entire planet may consist of crystallized carbon. Not a jewel in any ordinary sense, and far too hot to sparkle in the way we might imagine. But deep beneath its surface, vast lattices of carbon atoms could stretch for thousands of kilometers in every direction. It is a reminder of how wide the universe's range of possibilities truly is. A world of rock, a world of gas, and sometimes, quietly, a world of crystal. When we try to picture the universe, it is tempting to imagine it as something finite. A vast sphere with an outer boundary, an edge that could in theory be reached if one traveled far enough. But space does not appear to work that way. According to general relativity, the shape of space is determined by the matter and energy within it. And current measurements suggest that the universe is either genuinely infinite or so immeasurably large and gently curved that it folds back on itself, like the surface of a sphere, but in 3 dimensions. If that second possibility is true, you could travel in a perfectly straight line for as long as you wished, and eventually return to the place you started. Not by bouncing off a wall, not by turning around, but simply by following the curve of space itself back to its beginning. There is no edge to find, no boundary to press against. Just an unending continuity, a universe that contains everything, and beyond which there is simply nothing left to contain. Most stars are not born alone. They form in pairs or in clusters, emerging from the same vast clouds of gas and dust, shaped by the same gravitational forces. There is little reason to think our Sun was an exception. Some astronomers believe that when our star formed, more than 4 billion years ago, it had a companion, a twin born from the same collapsing cloud, orbiting the Sun at a great distance in the young solar system. Over time, the gentle gravitational influence of the Milky Way would have pulled them apart, sending the companion off on a different path through the galaxy. If this lost sibling still exists, it is out there somewhere, far beyond the reach of any current telescope, indistinguishable from the billions of other stars drifting through the galaxy on their quiet orbits. Some researchers have even speculated about a connection between this hypothetical companion, sometimes called Nemesis, and certain patterns in Earth's history. But the evidence for that remains thin. What lingers is simply the idea that our Sun, burning steadily and alone in our sky, may once have shared its beginning with another. When a massive star exhausts its fuel and collapses, what remains can be extraordinary. If the star was heavy enough, its core is compressed into an object roughly 20 kilometers across, about the width of a large city, yet containing more mass than our entire Sun. This is a neutron star. They cluster together under gravity, interact across millions of light years, and over time the larger ones draw in the smaller ones, not in sudden collisions, but in slow, inexorable processes that unfold across billions of years. When a small galaxy wanders too close to a larger one, tidal forces begin to work on it. The side of the smaller galaxy closer to the larger one feels a stronger gravitational pull than the far side. This differential force stretches the smaller system, drawing its stars into long streams and arcs that curve around the larger galaxy. Over successive orbits, the small galaxy is progressively dismantled, its stars stripped away and incorporated into the halo of the larger system, its gas absorbed, its structure dissolved. The Milky Way carries the evidence of this process in its own halo. Stellar streams, long, thin rivers of stars moving together through space, trace the paths of former satellite galaxies that have been disrupted and consumed over the past several billion years. Some of these streams arc across tens of thousands of light years, visible in sky surveys as coherent moving groups of stars whose common origin can be read from their shared trajectories and chemical compositions. The Milky Way is partly composed of galaxies that no longer exist as separate entities, absorbed so completely that they have become part of us, their stars now indistinguishable from our own, except to those who know precisely what to look for. Most black holes of stellar mass form where massive stars live, in the dense stellar populations of galactic disks, in star-forming regions, in the arms of spiral galaxies. And the matter inside it is unlike anything found naturally on Earth. After their formation, many remain where they were born, settling into the gravitational landscape of their host galaxy without dramatic displacement. But not all of them stay. In binary star systems, when the more massive star collapses into a black hole, the supernova explosion that precedes or accompanies the collapse can be asymmetric, releasing more energy in one direction than another. This asymmetry imparts a recoil to the newly formed black hole, kicking it out of its original orbit. Depending on the strength of the kick, it may escape the binary system entirely and drift away as a solitary object. A black hole with no companion, no orbit, no galaxy to anchor it, wandering through interstellar or even intergalactic space. Invisible, detectable only if it happens to pass near enough to another star to deflect its light or draw gas into a brief, revealing accretion disk. More massive black holes can be displaced through different mechanisms. When two galaxies merge, the supermassive black holes at their respective centers eventually find each other and spiral inward under gravitational wave emission. When they merge, the resulting gravitational wave burst can be asymmetric, delivering a recoil kick strong enough to eject the merged black hole from the galaxy entirely. Somewhere out there, in the dark between galaxies, black holes drift alone, carrying the mass of millions or billions of suns, entirely invisible, entirely free. Under the crushing weight of its own gravity, the ordinary structure of atoms breaks down entirely. When a star of modest mass, one like our Sun or somewhat more massive, exhausts the hydrogen and helium available for fusion, it sheds its outer layers in a slow, diffuse outflow, leaving behind its core. That core, compressed by gravity into an object roughly the size of Earth, is a white dwarf. White dwarfs are composed primarily of carbon and oxygen, the ash products of the nuclear burning that sustained the star throughout its life. At the temperatures and pressures prevailing in a white dwarf's interior, this carbon does not remain as a fluid. As the white dwarf cools over billions of years, the carbon atoms slow enough to settle into a regular lattice, crystallizing, layer by layer from the center outward, into a structure analogous to diamond. Astronomers have confirmed this process through observations of white dwarf pulsations, subtle oscillations in brightness that depend on the internal structure of the star and that change in a measurable way as crystallization progresses. In some white dwarfs, the crystallization is already well advanced. In others, it is just beginning. The end state, after billions of years of cooling, is an object the size of a planet, with the mass of a star composed of crystallized carbon, a diamond the size of Earth, dark and cold, drifting silently through space. No longer fusing, no longer radiating significantly, just slowly releasing the last of its warmth into the surrounding dark. Electrons and protons are pressed together so forcefully that they merge into neutrons, forming a kind of superfluid nuclear material packed to almost unimaginable density. A star reduced to its essence. Carbon, crystallized by time and gravity, adrift in the silent universe it once helped to illuminate. It is easy, contemplating 8 billion years, to feel that the universe has already lived most of its life. That number is genuinely vast by any human standard, more than 3 times the age of our planet, nearly 3,000 times the span of recorded human history. Measured against anything in our experience, it represents an incomprehensible depth of time. And yet, by the standards of the universe's full timeline, it is barely a beginning. The most numerous stars in the universe are red dwarfs, small, cool, extraordinarily frugal in their consumption of fuel. The least massive among them will burn steadily for trillions of years. Not billions. Trillions. A single teaspoon of it would weigh billions of tons. The universe at its current age of 8 billion years is, relative to the lifespan of these stars, roughly equivalent to the first few days of a human life. Beyond the stellar era, the universe's story continues. White dwarfs cool across timescales of quadrillions of years. Black holes evaporate over periods so vast that writing out their duration in years would require more digits than there are atoms in the observable universe. The heat death, if it comes, lies so far in the future that the present moment, stars still burning, galaxies still forming, minds still wondering, is indistinguishable from the very beginning. We exist early. The universe around us is young, active, and luminous. The long dark stretches almost unimaginably far ahead. What we are witnessing now, looking up at a sky full of stars, is the universe in the first light of its morning. A supernova is brief. If you were to imagine a single raindrop of neutron star material, just one small drop, it would be heavier than the entirety of Mount Everest. The collapse of a stellar core, the violent outward explosion of the outer layers, the peak of luminosity, these events unfold over seconds, hours, weeks. Then the light fades, the immediate drama concludes, and the site of the explosion appears, from a distance, to have quieted. But the supernova is not over. The shockwave produced by the explosion continues outward into the surrounding interstellar medium, sweeping up gas and dust as it travels, compressing and heating the material it encounters, accelerating particles to high energies, and illuminating its path with radiation across the electromagnetic spectrum. This expanding shell of shocked material, the supernova remnant, can continue to grow for thousands of years after the original explosion. As it expands, it slows. The shockwave encounters progressively more material, transferring its energy into the surrounding medium, and the remnant grows larger and more diffuse. Its structure becomes complex, filamentary, turbulent, shaped by the uneven distribution of the gas it sweeps through and by the magnetic fields it drags and amplifies as it moves. The Crab Nebula, one of the most studied objects in the sky, is the remnant of a supernova observed on Earth in the year 1054. Nearly 1,000 years later, it is still expanding outward at over 1,500 kilometers per second, still lit from within by the pulsar at its center, still forming new filaments, still spreading the heavy elements forged in its progenitor star into the interstellar medium. These objects are small, dark, extraordinarily dense, and in their silence they carry the compressed memory of a star's entire life, brought to a final state where matter has become almost indistinguishable from gravity itself. A star died 1,000 years ago. The consequences are still unfolding. Gravitational lensing, the bending of light by mass, is most dramatically visible on cosmic scales, where entire galaxy clusters act as lenses for the light of objects behind them. But the same physics operates at every scale where mass is present. Even something as comparatively small as a planet can bend light in a measurable way. When a planet passes almost exactly between a distant star and an observer on Earth, the planet's gravity acts as a tiny lens, focusing the background star's light and causing it to brighten briefly and then dim again as the alignment shifts. The brightening follows a precise, characteristic curve determined by the geometry of the alignment and the mass of the lensing object. This technique, called gravitational microlensing, has revealed planets that would be entirely undetectable by any other current method. Planets with no host star. Planets orbiting stars too faint for spectroscopic study. Light travels in straight lines. Planets in distant galaxies, detected not through any direct observation of the planet itself, but through the momentary distortion its gravity imprints on the light of an unrelated background star. The planet is dark. The planet may be cold. The planet may orbit a star we can barely see, in a galaxy we can barely resolve. But its mass is real. Its gravity is real, and as it drifts across the line of sight between a distant star and our instruments, it bends the light passing nearby just enough to announce its presence. A world revealing itself not through any light of its own, but through the subtle curvature it imposes on the light of something else entirely. In the earliest moments after the Big Bang, the universe was unimaginably hot, a plasma so dense and energetic that it was opaque to its own light. As it expanded, it cooled. And as it cooled, it passed through a series of states, each characterized by a different temperature, a different composition, a different relationship between matter and radiation. At approximately 380,000 years after the Big Bang, the temperature had dropped to around 3,000 degrees Kelvin, comparable to the surface temperature of a cool star. That much seems simple. At this temperature, electrons slowed enough to be captured by atomic nuclei, neutral atoms formed for the first time, and the universe became transparent. Light was free. At that moment, the entire universe glowed. Not in the invisible microwave radiation we detect today, but in visible light, warm orange-red light filling every point in space simultaneously. There was no outside from which to observe it. There was no dark sky. There was only the glow everywhere, in all directions, at every location. That light has been traveling and stretching ever since, cooling as the universe expanded around it, shifting from orange-red visible light through infrared and into the microwave frequencies we detect today as the cosmic microwave background. The glow that filled all of space has become a whisper, still present, still arriving from every direction, but stretched beyond visibility. The universe was once, briefly, a single vast lantern. But in a universe shaped by gravity, straight lines are not always what they appear to be. What remains of that light is now too cold and too long in wavelength for human eyes to see. But it is still there, all around us, in every direction, always. The cooling of the universe is not a simple, uniform process. It does not proceed like a pan of water removed from heat, losing temperature evenly across its entire volume at the same rate. The universe is structured, filled with matter arranged into galaxies, clusters, filaments, and voids. And that structure means that different regions cool at different rates. In galaxy clusters, vast quantities of hot gas, heated by the gravitational energy of infalling matter over billions of years, retain their warmth for enormous spans of time. The gas in the centers of massive clusters can remain at temperatures of tens of millions of degrees for billions of years, radiating slowly in X-rays, cooling only gradually despite the absence of any ongoing energy input. In the cosmic voids, by contrast, there is almost nothing to retain heat. The sparse gas there is thin and isolated, and it cools toward the background temperature of the cosmic microwave background with little delay. At the boundaries between structures, at the edges of filaments, at the outskirts of clusters, intermediate conditions prevail, with temperatures and cooling rates that reflect the local density and history of each particular region. In regions where gravity is especially intense, near massive galaxy clusters, for instance, space-time itself is curved. The universe does not dim all at once at the same rate everywhere. It cools the way a landscape cools on a clear autumn night. The open fields first, then the sheltered valleys, then the dense forests that hold their warmth into the early morning. Structured, uneven, shaped by local conditions. Even at the largest scales, the details matter. Among the more speculative but seriously entertained ideas in modern cosmology is the possibility that new universes can form within or alongside existing ones, not through any process we have observed, but through mechanisms that follow naturally from the physics of quantum fields and the geometry of space-time. One proposal, associated with the theory of eternal inflation, suggests that the quantum fields driving inflation can occasionally produce new regions of inflationary expansion, bubbles of space-time that pinch off from the parent universe and begin expanding independently, developing their own physical constants and laws inaccessible to any observer in the original universe. Another framework, proposed by the physicist Lee Smolin, imagines that black holes may give rise to new universes on the other side of their singularities, universes with slightly varied physical constants, subject to something analogous to natural selection across generations of cosmos. These ideas cannot currently be tested. They lie, perhaps permanently, beyond the reach of any conceivable observation, consequences of mathematics extended into regions that experiment cannot follow. Whether they describe something real or represent the point at which theoretical physics becomes something closer to philosophy remains genuinely uncertain. Light passing through these regions bends along that curvature, the way a beam passing through glass is redirected by the density of the material. But the possibility they raise is quietly extraordinary. That our universe, vast as it is, ancient as it is, might be one instance among many, and that somewhere, in the geometry of space-time itself, the conditions for another beginning may already be quietly assembling. In the first fraction of a second after the Big Bang, a period so brief that no unit of time in common use adequately describes it, the universe underwent a period of extraordinarily rapid expansion, called inflation. Space grew at a rate that dwarfs anything observable today, driven by the energy of a quantum field that has since decayed away. During inflation, quantum fluctuations in that field were stretched to cosmic scales, seeding the density variations that would eventually become galaxies. But inflation also produced another class of ripples, distortions not in the density of matter, but in the geometry of space-time itself. Primordial gravitational waves propagating through the fabric of the universe from the very first moments of its existence. These waves have been traveling ever since. They have been stretched by the expansion of the universe, just as light is stretched, into wavelengths far longer than when they were produced. They permeate all of space today, a background of gravitational radiation too faint for current instruments to detect directly. This effect is known as gravitational lensing, but their imprint may be visible indirectly. Primordial gravitational waves would leave a specific, subtle pattern in the polarization of the cosmic microwave background, a faint signature in the oldest light we can observe, encoding information about the energy scale of inflation and the conditions that prevailed in the universe's first instant. Several experiments are currently searching for this signal. If it is found, it will be a direct observational window into the very beginning, evidence of the moment when the universe was so young that no other record of it survives, and the only witnesses were the ripples still traveling through the space-time it made. Of all the facts gathered here tonight, perhaps the quietest and most extraordinary is this one. And it is not speculation. It is chemistry. Every hydrogen atom in your body was formed in the Big Bang, nearly 14 billion years ago. Every carbon atom was forged in the nuclear furnace of a star that lived and died before our sun was born. The calcium in your bones, the iron in your blood, the oxygen filling your lungs with each slow breath, all of it was synthesized in stellar interiors, scattered by supernova explosions into the interstellar medium, gathered over millions of years into the gas cloud that eventually collapsed to form our solar system, and incorporated through the processes of planetary formation and biological evolution into a living creature capable of lying still in the dark and wondering about the universe. One of its most striking consequences is that light from a single distant galaxy can reach us by more than one route, bent around a massive foreground object from different angles, arriving at our telescopes from different directions simultaneously. You are not separate from the cosmos. You are a part of it, a local arrangement of matter that the universe has, over nearly 14 billion years, organized into a form capable of perceiving itself. The light you have absorbed tonight, the facts that have drifted through your slowing thoughts, the quiet awareness still present somewhere between wakefulness and sleep, All of it is the universe in the act of knowing itself. There is no vantage point outside the cosmos from which to observe it. There is only matter arranged into minds, looking outward and inward simultaneously, finding in both directions something vast, something patient, and something that has been here in one form or another since the very beginning. The universe made you from itself, and in doing so, it gave itself eyes. And so we arrive gently at the end of tonight's journey. We have drifted through billions of years and billions of light years, past rogue planets spinning in the dark, past ancient stars carrying the chemistry of a younger cosmos, past the frozen echoes of sound waves that rang through the universe before atoms existed. We have visited the edges of what can be seen and stood quietly at the boundary of what can be known. We see not one image, but several. Somewhere in all of it, perhaps, a thought settled into stillness. Perhaps the facts blurred softly into one another. Perhaps the distances became not overwhelming, but restful, a reminder that the universe is far larger than any worry, far older than any difficulty, and far more patient than any restless mind. You are made of the same material as stars. You are warmed by the same kind of fusion that has been burning in the sky since before the Earth existed. The dark matter drifting through you right now has been part of this galaxy since before the sun formed. You are ancient in your atoms, even if your thoughts are new. Let that be enough for tonight. Let the galaxies keep their motion without your attention. Let the black holes evaporate across their trillions of years without your concern. Arcs, smeared ovals, and in rare cases of perfect alignment, complete rings of distorted light. Let the cosmos continue its slow, vast breathing, expanding, cooling, rearranging itself in the dark, while you rest. If these quiet journeys through the universe have helped you find your way to sleep, consider subscribing. There is always more to explore. One unhurried fact at a time, one slow breath at a time, in the company of a universe that has never once been in a hurry. Good night. In a few remarkable instances, astronomers have observed light from the same distant supernova arriving through different gravitational paths, the explosion appearing to occur more than once, at different moments, as each beam of light completed its separate journey. Even light, it turns out, can take the long way home. The very first stars were unlike anything that exists in the universe today. They were born into a cosmos containing only the simplest elements, hydrogen and helium, left over from the Big Bang, with no heavier atoms yet in existence. With no metals to absorb radiation and slow their collapse, these stars grew enormous. Some may have been hundreds of times more massive than our sun. They burned accordingly, blazing through their fuel at a rate that would seem almost wasteful by the standards of later stars, shining perhaps 1,000,000 times more brightly than our own. And because they burned so hot and so fast, they did not last long. After only a few million years, a brief moment on cosmic timescales, they exhausted themselves and collapsed in spectacular explosions. But in their short lives, they changed everything. Their explosions seeded the surrounding gas with the first heavy elements ever created: carbon, oxygen, iron, the building blocks of all that would follow. They lit up their surroundings. They began the long process of cosmic evolution that would eventually, billions of years later, lead to planets, oceans, and the quiet wandering of minds like yours. Their light is gone, but their work remains, written into the chemistry of everything. Right now, as you lie still, something is passing through you. Not through the room, not around you, but directly through your body, through the mattress beneath you, through the floor, through the earth itself. Trillions of particles, every second without pause. These are dark matter particles, and you will never feel them. Dark matter does not interact with light. It does not emit, reflect, or absorb it. It cannot be seen, touched, or tasted. But it has mass, and it responds to gravity, and it is everywhere. Our galaxy is embedded within a vast halo of it, an invisible sphere extending far beyond the visible stars. As Earth moves through this halo on its orbit, an almost incomprehensible number of dark matter particles stream through every square centimeter of everything, including you. They pass through without collision, without friction, without leaving any mark at all. We still do not know what dark matter is made of. We know it exists because of the gravitational influence it exerts on the things we can see. Without it, galaxies would not hold together. The cosmic structures we observe would never have formed. The universe would be a very different place. And yet it moves through you, silently and continuously, even as you sleep. Not every galaxy blazes with the light of billions of stars. Some are barely there at all. Astronomers have discovered entire galaxies, systems with the mass and breadth we associate with galaxies, that contain almost no stars. They are rich in gas and dark matter, but show little evidence of star formation, past or present. Some appear only as faint smudges at the limits of the deepest sky surveys, visible only because of their diffuse glow in certain wavelengths of light. How a galaxy forms and yet fails to build stars remains one of the quieter puzzles in cosmology. Perhaps these systems were stripped of their cold gas early in the universe's history, before star formation could take hold. Perhaps they were heated by radiation from neighboring galaxies, or disrupted by gravitational encounters that scattered their material before it could condense. Whatever the cause, these dim systems persist. They drift through space holding their mass quietly, not blazing but simply existing. Gravitational presences without the light we usually use to find them. They remind us that not every galaxy announces itself. Some simply endure in the dark, patient and unseen. In the cosmic microwave background, that faint ancient glow left over from the Big Bang, the temperature is remarkably uniform across the entire sky. The variations that do exist are tiny, no more than fractions of a degree. And yet within that near-perfect smoothness, there is one region that does not belong. A cold spot. Significantly colder than its surroundings, and far larger than current models of the early universe would lead us to expect. It spans hundreds of millions of light years, and its presence sits uncomfortably with our best understanding of how the young universe should have looked. Several explanations have been proposed. Some astronomers suggest it may be the imprint of an enormous cosmic void, a vast underdense region of space through which the ancient light passed, losing energy along the way. Others have wondered whether it could hint at something stranger still. Perhaps the faint scar left by a collision between our universe and another in the earliest and most violent moments of inflation. No explanation offered so far accounts for it fully. The cold spot remains, a quiet anomaly written into the oldest signal in the sky. Not loud enough to overturn cosmology, but persistent enough to suggest that something, somewhere in our understanding, may not yet be complete. Every year, the moon moves a little further from Earth. Not by much, roughly 3.5 centimeters, approximately the rate at which your fingernails grow. It is not something you could measure in a lifetime with your eyes. But over billions of years, it accumulates into something profound. When the moon first formed, around 4.5 billion years ago, it orbited much closer to Earth. So close that it would have appeared enormous in the sky. And because of that closeness, the tidal forces between the two bodies were far stronger. A day on the early Earth lasted only a few hours. The planet spun rapidly beneath a moon that loomed large overhead. Over time, the interaction between the moon's gravity, Earth's oceans, and the friction of tidal movement transferred rotational energy from Earth into the moon's orbit, gradually pushing it outward. The process continues today, imperceptibly, always. In the very distant future, Earth and the moon may become tidally locked, each showing the same face to the other in a permanent, motionless gaze. But that moment is far away. For now, the moon keeps its slow retreat, night by night, year by year, slipping a little further into the dark. In some parts of the galaxy, stars do not live alone. They are born in pairs, orbiting one another across distances that can range from vast to nearly nothing. And when two stars orbit closely enough, something extraordinary can happen. Their outer layers begin to touch. As one star evolves and swells, its outer envelope can spill over toward its companion. drawn by gravity into a slow, spiraling transfer of material. Sometimes this exchange is gradual and steady, building quietly over millions of years. Other times it triggers sudden events, bursts of brightness, rapid changes in rotation, even a complete merger of the two stars into one. The physics of these systems is intricate. One star may be stripped down to a hot, glowing core, while the other becomes bloated and enriched. Their futures are bound together from the moment the transfer begins. Some of the most unusual objects in the universe, certain types of supernova, compact neutron star pairs, millisecond pulsars, trace their origins back to these quietly intimate systems. Two stars locked in orbit, close enough to share themselves with one another. A slow, continuous embrace played out across millions of years. Travel far enough from any star, any galaxy, any drifting grain of dust, and you might expect to find perfect emptiness. Pure nothingness. A void so complete that there is simply nothing left to speak of. But according to quantum physics, that void does not exist. Even in the deepest, most remote regions of space, the fabric of reality is restless. Pairs of particles and antiparticles spontaneously flicker into existence and annihilate almost immediately, too briefly to observe directly, but real enough to have measurable consequences. These quantum fluctuations fill all of space, at all times without exception. They are not merely theoretical curiosities. They influence the behavior of nearby particles. They contribute to the energy content of empty space itself. And they are thought to play a role in dark energy, the mysterious force that is currently driving the accelerating expansion of the universe. So the deepest silence in the universe is not truly silent. The emptiest place is not truly empty. Beneath the apparent stillness of the void, something is always happening. A constant, invisible trembling at the very foundation of reality. We tend to experience time as something steady and universal. A second here is a second everywhere. A clock on one side of the universe ticks at the same rate as a clock on the other. It feels like the most basic assumption we could make about reality. But it is not correct. According to Einstein's general theory of relativity, time is not separate from space. It is woven together with it into a single fabric, and that fabric is distorted by gravity. Where gravity is strong, near a massive planet, near a dense star, near a black hole, time flows more slowly relative to regions where gravity is weaker. This is not a metaphor or an approximation. It is a measurable physical effect, confirmed by atomic clocks, by GPS satellites, by careful experiments conducted here on Earth. Some cosmologists go further, asking whether time could also vary across much larger scales, whether the uneven distribution of matter in the early universe might have left different regions expanding and cooling at subtly different temporal rates. The full answer remains uncertain. But what is clear is this: time, which feels so absolute and unwavering, is in reality a flexible thing, shaped by the space through which it flows and by the mass of the objects it moves around. When we picture our galaxy, we tend to imagine the spiral, great sweeping arms of stars and gas and dust, lit from within by billions of suns, turning slowly in the dark. It is a beautiful image, and it is, in a sense, accurate. But it is also deeply incomplete. Surrounding the visible disk of the Milky Way is a vast, mostly invisible structure called the galactic halo. It extends far beyond the spiral arms, reaching distances many times greater than the width of the disk itself. And it contains ancient globular clusters, stray stars flung out from the main body of the galaxy, diffuse clouds of hot gas, and enormous quantities of dark matter. We cannot see the halo directly. We infer its presence through the motion of stars and the bending of light passing through regions it occupies. It shapes the galaxy's gravitational structure, stabilizes its rotation, and carries within it the accumulated record of billions of years of mergers and collisions with smaller galaxies. The spiral we see is bright and beautiful, but it is simply the luminous center of something far larger, a glowing heart wrapped in invisible arms, stretching out into the dark in every direction. The universe is approximately 13, 8 billion years old. Light travels at a fixed speed. And so the further out we look into space, the further back in time we see, because the light reaching our instruments left its source long, long ago. Using the James Webb Space Telescope, astronomers have now detected light from a galaxy that existed just 200 million years after the Big Bang. On the timescale of the cosmos, that is extraordinarily early, less than 2% of the universe's current age. That light has been traveling toward us for more than 13.5 billion years. It has crossed an expanding universe, been stretched by the growth of space, and finally arrived at a mirror floating in the cold beyond Earth's atmosphere. The galaxy it came from is small and faint by modern standards, primitive in its structure, but it carries within its spectrum clues about the conditions that existed when the first structures were just beginning to assemble from the primordial darkness. Observing it is something like finding a single page from the universe's earliest chapter, fragile, faded, and extraordinary. When astronomers chart the positions of galaxies across enormous volumes of space, something unexpected emerges from the data. Galaxies are not scattered randomly. They cluster along vast filaments, thread-like structures stretching across hundreds of millions of light-years, with immense empty voids lying between them. This interconnected architecture is called the cosmic web. And when you step back far enough to take it all in, it bears a striking resemblance to something much closer to home. It looks like a brain. Dense nodes where filaments intersect resemble neurons. The filaments themselves resemble the axons connecting them. The voids between are like the spaces between clusters of cells. The structural similarity between the largest thing we know and the organ through which we know it is, at minimum, a remarkable coincidence. Of course, the universe is not thinking. There is no consciousness in the filaments, no meaning in the nodes. The resemblance is purely geometric, two very different systems, shaped by entirely different physics, arriving at a similar pattern through completely unrelated processes. And yet it is quietly astonishing to look at the largest structure in existence and find, looking back, something that resembles the shape of thought. There is no sound in space, no medium for pressure waves to travel through, no air to carry a vibration from one place to another. And yet stars are not silent, not entirely. Deep within their interiors, sound waves move. Pressure pulses ripple through the dense plasma of a star's inner layers, bouncing between boundaries, setting the entire structure into slow, subtle oscillation. These are not sounds that could ever reach a human ear. They are far too low in frequency, far too vast in scale. But they are real, and they leave traces. As a star pulses inward and outward, its surface brightness shifts almost imperceptibly. With sensitive instruments, scientists can detect these variations and work backward, using the pattern of oscillations to map what lies beneath the surface. The density of inner layers, the rate of internal rotation, the presence of hidden flows of hot gas, all of it becomes readable through the vibrations. This field is called astroseismology, and it has transformed our ability to understand stellar interiors. Each star has its own characteristic frequencies, as distinctive as a fingerprint, determined by its size, composition, and age. The stars do not broadcast their inner lives. But for those who know how to listen, they have never stopped speaking. Galaxies are not assembled in a single moment. They grow over time, pulling in gas, merging with smaller systems, accumulating stars from a dozen different sources across billions of years. A galaxy, as we observe it today, is the result of a long and complicated history of collisions, absorptions, and gradual accretion. This means that some of the stars within a galaxy can be older than the galaxy's current form. They may have originated in earlier, smaller galaxies that were later consumed and dissolved into a larger structure. Their orbits, their chemistry, and their ages all reflect a time before the galaxy that now contains them had fully assembled. These ancient stars are often found in globular clusters, tightly bound, roughly spherical groups that orbit in the outer regions of galaxies, far from the busy disk. Some of them are over 13 billion years old, formed when the universe itself was only a few hundred million years old. They carry the chemical signature of that early era. Fewer heavy elements, a simpler composition, the mark of a cosmos still in its infancy, before generations of stellar explosions had seeded space with the richer chemistry we find today. These stars are quiet survivors, fossils of a time before the galaxy existed in any form we would now recognize. Everything we understand about galaxies suggests that dark matter is essential to them. It provides the gravitational scaffolding that holds them together. It explains why stars in the outer regions of galaxies orbit faster than the visible mass alone would allow. It is, in the standard model of cosmology, as fundamental to a galaxy as the stars themselves. And then astronomers found galaxies without it. In recent years, a small number of galaxies have been observed whose stars move exactly as you would predict if only the visible matter were present, with no dark matter contribution at all. These galaxies do not behave the way they should. They do not fit comfortably into the models we rely on, and their existence has not yet been fully explained. Some researchers suggest their dark matter was stripped away during ancient gravitational encounters with larger neighbors. Others propose that our understanding of dark matter, or of gravity itself, may still be incomplete in ways these galaxies are beginning to reveal. Either way, these systems sit quietly at the edge of our understanding. Not dramatic, not loud, just slightly, persistently wrong in a way that suggests the universe still has something left to teach us. Nothing can move through space faster than light. This is one of the most fundamental constraints in physics, confirmed by every experiment ever designed to test it. It is not a limitation that technology might one day overcome. It is written into the structure of reality itself, and yet the universe has found a way around it. Space itself is not bound by this rule. During the first extraordinary moments after the Big Bang, the universe expanded so rapidly that distant regions were pulled apart faster than light could have traveled between them. This was not matter moving through space, it was space itself growing, stretching the distances between everything simultaneously. That process continues today, in a gentler form. The universe is still expanding, and galaxies that lie far enough away are receding from us at speeds that exceed the speed of light, not because they are moving quickly through space, but because the space between us and them is stretching faster than light can cross it. This is why the observable universe has a boundary. Beyond a certain distance, galaxies are receding so fast that their light will never reach us. The universe grows calmly and continuously, carrying some of its contents permanently beyond our sight. It is easy to picture the solar system as a neat diagram, planets tracing tidy circles around a stationary sun, everything in its place, everything still except for the orbital motion. It is a useful picture, but it leaves out something important. The sun is not still. It is moving, orbiting the center of the Milky Way at nearly 1,000,000 kilometers per hour, completing one full circuit of the galaxy roughly every 225 million years. And as it moves, the planets follow. Not just circling the sun, but sweeping through space behind it, tracing paths that are not circles at all. The combined motion, orbital around the sun and solar movement through the galaxy, produces something closer to a corkscrew, a helix. Each planet spiraling forward through space, winding its way along a path that never quite returns to the same point. And the Milky Way itself is moving too, falling through the larger structures of the universe toward concentrations of mass we are still mapping. There is no stillness anywhere in this picture. No fixed point. Only motion layered upon motion, orbit within orbit, a dance so vast and so gradual that we feel none of it. And yet it carries us, every moment, somewhere we have never been before. Go far enough from any star, any galaxy, any source of heat or light, and you might expect the temperature to drop toward absolute zero, the point at which all thermal motion ceases and nothing remains. It almost does, but not quite. Even in the deepest, most remote regions of intergalactic space, a faint warmth persists. The temperature of the universe's emptiest places sits at approximately 2.7 Kelvin, just a few degrees above absolute zero, Cold beyond anything we naturally encounter on Earth. Cold enough to freeze every gas except helium, and yet measurably, irreducibly, not zero. This residual warmth is the cosmic microwave background, the stretched and cooled remnant of light released when the universe was 380,000 years old. That ancient glow has been diluting and cooling for more than 13 billion years, and it now permeates all of space equally, in every direction, at every point. No matter where you go in the universe, you are never entirely free of it. It is the thermal memory of the Big Bang itself, still present in the void, still measurable, still real. In the far future, it will cool further still, but it will never quite reach zero. Even in the greatest emptiness, the echo of creation persists. At the smallest conceivable scales of reality, far smaller than atoms, far smaller than protons, smaller than anything we can directly observe, the universe does not behave predictably. At these scales, energy fluctuates randomly and constantly. Tiny ripples of existence appear and vanish in intervals so brief they have no meaningful duration. In ordinary circumstances, these fluctuations are inconsequential. They come and go without leaving a mark on anything we can perceive. But in the first moments after the Big Bang, circumstances were not ordinary. The universe underwent a period of extraordinarily rapid expansion called inflation, a brief interval during which space grew at a rate that dwarfs anything we observe today. And during that expansion, quantum fluctuations were caught and stretched, magnified from the subatomic to the cosmic, imprinted onto the fabric of space itself at scales large enough to matter. Those frozen fluctuations became slight variations in the density of matter, regions fractionally denser than their surroundings. And over hundreds of millions of years, gravity did the rest, pulling matter toward those denser regions, building the first structures, the first stars, the first galaxies, the filaments and voids of the cosmic web, the galaxy you live in, the star your planet orbits. All of it traces back, in an unbroken chain of cause and effect, to random tremors in the void at the beginning of time. Not every star ends suddenly. Some spend their final eras in a long, slow rhythm, expanding and contracting, brightening and dimming, in cycles that can last days, months, or even years. These are variable stars, and their pulsations arise from changes within their outer layers. As the star's outer envelope expands, it cools and becomes more transparent, allowing more light to escape. Then gravity draws it back inward. It compresses, heats, and brightens again. The cycle repeats, steady and measurable, like a vast slow breath. Some of these stars pulse with remarkable regularity. So regular, in fact, that their periods can be used to calculate distances, because the relationship between a variable star's pulsation period and its true luminosity is well understood. Measure how long the cycle takes, and you can determine how bright the star truly is. Compare that to how bright it appears, and the distance follows directly. Variable stars have served as some of astronomy's most reliable distance markers, used to map the scale of the Milky Way and the distances to nearby galaxies. They are stars in their final chapters, but they are not going quietly. They are keeping time, slowly and steadily, broadcasting their presence across the dark with every long, luminous breath. If you could somehow perceive the full range of electromagnetic radiation, not just visible light, but radio waves, X-rays, and the infrared glow of warm gas, the space around our solar system would look very different from what we usually picture. We are not drifting through average interstellar space. We are inside a bubble. The local bubble, as it is called, is a region of unusually low density, high temperature gas stretching several hundred light years in every direction around us. It is thought to have been carved out over millions of years by a series of ancient supernova explosions, massive stars that ended their lives in violent outbursts, blasting shock waves outward through the surrounding gas and clearing a cavity in the interstellar medium. The walls of this bubble are marked by a denser shell of gas and dust, glowing faintly in X-ray wavelengths. Inside, the gas is thin and hot, too diffuse to block much light, but detectable by the right instruments. We feel none of this directly. Our daily experience of Earth gives no hint that we sit within a vast, irregularly shaped remnant of ancient stellar violence. But the bubble is there, a quiet chamber around us, born from catastrophe, now simply the backdrop of our cosmic neighborhood. Our galaxy is not sitting still. Neither is the local group, the collection of dozens of galaxies of which the Milky Way is a part. All of it is moving, drifting in a particular direction through the larger structure of the universe, pulled by gravitational forces operating across hundreds of millions of light years. Much of that pull comes from a region known as the Great Attractor, a massive concentration of galaxies and dark matter lying roughly 250 million light-years away, in a direction that happens to be partially obscured by the dense plane of our own galaxy. For decades, astronomers knew something was pulling nearby galaxy clusters in that direction without being able to see clearly what it was. But the story does not end there. On the opposite side of our motion lies a vast, unusually empty region of space, a cosmic void so devoid of matter that its very emptiness creates a kind of negative gravitational pressure. Galaxies are not drawn toward it. They are, in effect, pushed away from it. This region is called the Dipole Repeller. Together with the Great Attractor, it helps explain the direction and speed of our local galactic motion. Pulled from one side by the weight of unseen mass and nudged from the other by the absence of it. We drift between them quietly at speeds too vast to feel and too slow to notice. Right now, without any sensation, without any signal your body could possibly detect, you are being passed through. Neutrinos are among the most abundant particles in the universe. They are produced in enormous quantities by the nuclear reactions burning inside the sun, by exploding stars, by radioactive decay, and by processes that occurred in the first moments after the Big Bang. They travel at nearly the speed of light and carry almost no mass. And they interact with ordinary matter so rarely that the entire Earth presents barely any obstacle to them at all. Every second, trillions of neutrinos stream through every square centimeter of your body. They enter through one side and exit through the other without deflection, without deposit, without leaving any trace that they were ever there. If you could somehow perceive them, the sun would be blazing from below your feet at midnight, just as brightly as it shines overhead at noon, because the Earth itself barely slows them. We study neutrinos using detectors buried deep underground, shielded from other particles, waiting patiently for the rare moment when a neutrino collides with an atom and produces a faint, measurable flash. Most simply pass through. Most always will. The universe is full of motion that leaves no mark, full of presence that asks nothing of us, and gives nothing in return except its quiet, continuous existence. We tend to picture the death of a massive star as something spectacular. A supernova, a sudden brilliant outpouring of light so intense it can briefly rival an entire galaxy, visible across billions of light years, leaving behind an expanding cloud of glowing debris and a dense remnant at its core. But for the most massive stars of all, the end can be something else entirely. When a star above a certain mass threshold exhausts its fuel, the collapse of its core can be so rapid and so complete that gravity overwhelms everything before any outward explosion has a chance to form. The outer layers, rather than being blasted into space, simply fall inward. The star does not go out in a blaze. It simply disappears. Astronomers have observed candidates for exactly this process. Stars that were present in one image of a distant galaxy and absent in the next, with no intervening flash of light to mark the transition. One moment, a star. The next, nothing. Just an absence where something large and bright used to be. These events are called direct collapses, and what they leave behind is a black hole formed not from the dramatic remnants of an explosion, but from a quiet, total surrender to gravity. Not all endings announce themselves. Some simply stop. We sometimes think of galaxies as isolated, island universes separated by such vast distances that they exist in a kind of permanent solitude. But many galaxies live in groups, bound together by gravity, interacting across spans of time that dwarf anything in human experience. Our own Milky Way is surrounded by a retinue of smaller companions. Dozens of satellite galaxies orbit at varying distances, tracing long elliptical paths that carry them out into the halo and back again over billions of years. The most prominent of these, the Large and Small Magellanic Clouds, are visible from the southern hemisphere as detached patches of light, close enough that their gravitational interaction with the Milky Way has already begun to distort their shapes and draw streams of gas between them. As these smaller galaxies move, the tidal forces of the larger one reach out and pull at them, drawing stars away in long arcs, creating stellar streams that stretch across millions of light years. Over enough time, a small galaxy may be absorbed entirely, its stars dispersed into the halo of the larger galaxy, its identity dissolved. It is not violent. It is not sudden. It is simply the slow, patient work of gravity, gathering what is nearby, holding what it can, and eventually drawing everything inward. Among the most extreme objects in the universe is a rare and short-lived thing called a magnetar, a neutron star endowed with a magnetic field of almost incomprehensible strength. While Earth's magnetic field is sufficient to deflect a compass needle, a magnetar's field is trillions of times more intense, strong enough to distort the shapes of atoms themselves, to tear matter apart at a distance, to strip electrons from their nuclei across thousands of kilometers. When the right kind of massive star collapses and forms one of these objects, the result can be one of the most energetic explosions the universe is capable of producing. If the magnetar forms rapidly and releases its enormous rotational and magnetic energy in a short time, it can drive an outburst far more powerful than an ordinary supernova, a magnetar hypernova, capable of briefly outshining every other star in its host galaxy combined. These events are thought to be responsible for some of the most powerful gamma-ray bursts ever detected, flashes of high-energy radiation that travel across billions of light-years and arrive at our instruments carrying information about catastrophes that occurred long before Earth existed. The explosion lasts only seconds. Its light crosses the universe for billions of years, and at its origin was a small, dense, magnetically furious object collapsing in on itself, the most intense physics the cosmos can arrange. Look in any direction for long enough, with powerful enough instruments, and you will eventually reach a limit. Not a wall, not a boundary marked by anything physical, just a distance beyond which the light has not yet had time to reach us. This is the edge of the observable universe, a sphere roughly 46 billion light-years in radius, centered on Earth, encompassing everything we can in principle detect. Beyond it, the universe almost certainly continues. But the light from those regions, even traveling at the maximum speed physics allows, has not yet crossed the distance to us in the 8 billion years since the Big Bang. The boundary is not fixed forever. In a universe that were not expanding, it would grow over time as light from more distant regions gradually arrived. But our universe is expanding, and that expansion is accelerating. Some regions beyond the current horizon are receding fast enough that their light will never reach us, not in any amount of time. So the observable universe is not simply a temporary limitation we might one day overcome. For some portions of what lies beyond, the horizon is permanent. What we can see is not all there is. It is only all there will ever be available to us, a finite window onto something that may be infinite, growing slowly darker at its edges as the universe quietly carries more of itself beyond our reach. At the heart of many large galaxies lies a supermassive black hole, an object millions or billions of times the mass of our Sun, surrounded by a swirling disk of gas and dust, spiraling slowly inward. Most of the material in this disk eventually crosses the event horizon and is lost. But not all of it. In some galaxies, the conditions around the black hole generate powerful magnetic fields that redirect a portion of the infalling material outward, accelerating it to near the speed of light and blasting it away from the galaxy in two narrow opposite jets. These jets can carry more energy than the combined output of billions of stars, and they do not stop at the edge of the galaxy. They continue outward for millions of light years. Far beyond the stars, far beyond the gas clouds, out into the intergalactic medium, where they eventually slow and spread into vast, diffuse lobes of radio-emitting plasma. These structures, called radio galaxies for the wavelengths in which their jets are most visible, represent some of the largest individual structures in the universe. Their scale is almost impossible to hold in the mind. And at the origin of each one is a black hole, an object so dense that light cannot escape it, producing from that very darkness some of the most powerful and far-reaching outflows the cosmos has ever made. The Milky Way turns. Hundreds of billions of stars, most of them, orbit the galactic center in roughly the same direction, following the rotation of the galaxy like leaves caught in a slow, vast current. It is one of the quiet regularities of the cosmos, a pattern maintained across distances and timescales that beggar imagination. But not every star follows the current. At least one known star, a relatively unremarkable object by most measures, travels in the opposite direction. Its orbit is retrograde, cutting against the flow of the galaxy's rotation in a path that carries it repeatedly through regions populated by stars moving the other way. How it came to move this way is not entirely certain. One possibility is that it originated in a smaller galaxy that was absorbed by the Milky Way long ago, a galaxy that rotated differently and whose stars retained that older motion even after their home was dissolved into the larger structure. Another possibility is a gravitational interaction of sufficient violence to reverse its orbit entirely, a near encounter with a massive object that flung it onto its current contrary path. Whatever the cause, it moves as it moves. Steady, solitary, going its own way through a galaxy that flows around it in the other direction. A quiet reminder that even in the most orderly systems, there are always those that do not follow the general rule. It sounds at first like something invented, but it is documented, peer-reviewed, and real. Astronomers studying the chemical composition of a large molecular cloud near the center of the Milky Way, a region called Sagittarius B2, identified a molecule known as ethyl formate among the hundreds of compounds present in the gas. Ethyl formate is the compound primarily responsible for the characteristic flavor of raspberries. It is also found in rum. The galactic center does not, of course, actually smell like anything. Space is a vacuum. There is no medium to carry a scent, no way for those molecules to reach a nose, no sensation to be had at any distance. The discovery is a chemical one, not a sensory one. But what it points to is genuinely remarkable. The interstellar medium, the gas and dust between stars, is not chemically inert. It is rich with organic molecules. Alcohols, aldehydes, amino acid precursors, sugars. The building blocks of biological chemistry, assembling themselves in the cold dark between the stars through processes that require no biology, no intention, and no warmth. Life has not been found in these clouds, but the chemistry that life requires appears to be written into the cosmos at a fundamental level, distributed throughout the galaxy, forming in the dark, waiting in the spaces between everything. The Andromeda Galaxy is our nearest large galactic neighbor, a vast spiral containing perhaps 1 trillion stars, lying approximately 2.5 million light-years away. For most of human history, that distance seemed to place it firmly in the category of the unreachably remote. But Andromeda is approaching. It has been approaching for billions of years, drawn toward the Milky Way by the mutual gravitational attraction between two of the largest members of the local group. In roughly 4 billion years, the two galaxies will begin their full merger, a slow blending of stars, gas, and dark matter that will reshape both systems into something new. What is less commonly appreciated is that the merger has, in a sense, already begun. Both galaxies are surrounded by vast halos of hot gas and dark matter extending far beyond their visible disks. These halos, diffuse, largely invisible but massive, have already grown large enough to overlap. The outermost regions of the Milky Way and Andromeda are already in contact, already exchanging material at the boundaries where their halos meet. The collision in 4 billion years will be dramatic in its way. But it will be the continuation of something that started long before any star in either galaxy notices. Two great systems, reaching toward each other across the dark, already touching at their edges. A supernova is one of the most luminous events the universe produces. For a brief period, a single dying star can outshine the entire galaxy it inhabits. Billions of stars overwhelmed by the light of one. It is the kind of ending that announces itself across billions of light years. But some stellar deaths produce almost no light at all. When a massive star's core collapses and the conditions are not quite right for an outward explosion to propagate through the outer layers, those layers do not fly apart. Instead, they fall inward. The energy that would otherwise power a supernova, the heat, the radiation, the pressure wave, is swallowed by the forming black hole before it can escape. From a distance, the star simply disappears. No flash, no brightening, no expanding remnant. Just an absence. A star that was there and then was not. Astronomers have identified candidates for these failed supernovae, massive stars in other galaxies that vanished from monitoring surveys without any accompanying burst of light. The black holes they leave behind are invisible, as black holes are. The only evidence of what occurred is the star's sudden absence from images taken days or weeks apart. Some of the universe's most massive objects form not with a blaze, but in complete and total silence. When two black holes find themselves bound together, orbiting one another across years and decades and millennia, something slow and inevitable begins. With each orbit, they radiate energy outward in the form of gravitational waves, ripples in the fabric of space-time propagating away from the pair at the speed of light. And as that energy leaves, the orbit shrinks. Gradually, over timescales that may span millions of years, the two objects spiral closer. Their orbits tighten. The gravitational waves they emit grow stronger and more frequent. And then, in a final fraction of a second, they merge, two black holes becoming one in an event that releases more energy than entire galaxies emit in light over millions of years. None of this produces any light. There is no flash, no visible explosion, no electromagnetic signal of any kind. The merger is invisible to any telescope. The only trace it leaves is a brief specific pattern of gravitational waves, a chirp in the geometry of space itself, spreading outward in all directions at the speed of light. In 2015, instruments on Earth detected one of these signals for the first time, a wave that had traveled more than 1 billion light-years, arriving as an almost imperceptible stretching and squeezing of space. It confirmed a prediction Einstein had made a century earlier, without any way to test it. Two invisible giants collided somewhere in the distant universe, and the universe whispered about it quietly across 1 billion years of space. When a star like our Sun reaches the end of its life, it does not go suddenly. It swells first into a red giant, expanding outward until it has engulfed its inner planets. Then its outer layers drift away into space, dispersing into a glowing shell of gas called a planetary nebula. What remains at the center is a dense, hot remnant, a white dwarf. A white dwarf is roughly the size of Earth, but contains roughly the mass of the Sun. It is no longer undergoing fusion. It produces no new energy. It simply holds the heat accumulated over its lifetime and releases it very slowly into the surrounding dark. The rate of cooling is almost imperceptibly slow. A white dwarf cools over billions of years, gradually dimming from white to yellow to orange to red, and eventually to a cold, dark remnant called a black dwarf. Invisible, inert, composed of crystallized carbon and oxygen drifting silently through space. No black dwarfs yet exist. The universe is not old enough. Every white dwarf ever formed, and there are many, is still somewhere in the process of cooling, still faintly glowing, still releasing the warmth of a life already finished. The death of a small star is not an event. It is a process, slow, patient, and measured not in seconds or years, but in the deep time of the cosmos itself. Einstein's general theory of relativity makes a prediction that seems, at first encounter, almost too strange to accept. Time does not flow at the same rate everywhere. In regions of stronger gravity, time runs more slowly relative to regions where gravity is weaker. This is not a perceptual illusion, not a metaphor for something more prosaic. It is a physical reality, confirmed by measurement. Near a black hole, this effect becomes extreme. For an observer hovering just outside the event horizon, the boundary within which escape becomes impossible, time would pass at an almost incomprehensibly reduced rate compared to time experienced far away. A distant observer watching that hovering figure would see them slow almost to a standstill. Minutes near the black hole could correspond to years or decades or centuries elsewhere in the universe. At the event horizon itself, from the perspective of a distant observer, time appears to stop entirely. An object falling inward seems to freeze at the boundary, its image dimming and redshifting, never quite crossing. This is not science fiction assembled from loose analogies. The milder version of this effect has been measured directly. Atomic clocks at different altitudes on Earth tick at measurably different rates, and the GPS satellites orbiting above us require corrections for exactly this phenomenon to maintain their accuracy. Near a black hole, the effect simply becomes as large as the gravity that causes it. Between the great filaments and clusters of the cosmic web lie regions of almost unimaginable emptiness. These are the cosmic voids, vast stretches of space where galaxies are rare or absent, where gas is thin beyond measure, where almost nothing interrupts the silence for hundreds of millions of light years in every direction. In these voids, the temperature drops to approximately 2.7 Kelvin, a few degrees above absolute zero. This is the temperature of the cosmic microwave background, the faint thermal residue of the Big Bang that permeates all of space. In the voids, where there are no stars to contribute heat and almost no matter to retain it, that background radiation represents virtually the entirety of the thermal energy present. It is colder than anything that occurs naturally on Earth, colder than the surface of Pluto, colder than the interior of most scientific laboratories working at the frontier of low-temperature physics. And these regions are not small. A single cosmic void might span 300 or 400 million light-years. The emptiness is not a gap between things. It is a structure in its own right, a vast, cold, silent domain occupying the majority of the universe's volume while containing a small minority of its matter. The universe is mostly empty, and that emptiness is very, very cold. In the first hundreds of thousands of years after the Big Bang, the universe was opaque. Photons could not travel freely, they were constantly scattered by the dense fog of free electrons and nuclei that filled all of space. Light existed, but it could not go anywhere useful. The cosmos glowed, but nothing within it could see. Then, as the universe expanded and cooled to around 3000 degrees Kelvin, electrons slowed enough to be captured by atomic nuclei. Neutral atoms formed for the first time, and suddenly the fog lifted. Light was free to travel. The universe became transparent, and the cosmic microwave background was released. The light from that moment of clearing, still detectable today. But the story did not end there. As the first stars and galaxies formed, they poured ultraviolet radiation into the surrounding gas, stripping electrons from neutral hydrogen atoms, once again in a process called reionization. The universe went through a second transformation, becoming not just transparent, but ionized throughout, a state it largely remains in today. And as matter continues to spread out across the expanding universe, there is progressively less between any 2 points to obstruct the passage of light. The cosmos that was once a glowing, impenetrable fog has become an open, nearly unobstructed expanse. Space has been clearing for 13 billion years. Every photon traveling through it today does so with a freedom that was not always guaranteed. For most of human history, black holes were purely theoretical objects. Then they became objects we could infer from indirect evidence: the motion of nearby stars, the behavior of gas spiraling inward, the gravitational waves produced by mergers. But for a long time, no one had ever seen one directly. In 2019, that changed. The Event Horizon Telescope, not a single instrument, but a coordinated network of radio telescopes distributed across the surface of the Earth, functioning together as a single planet-sized detector, captured the first direct image of a black hole's immediate environment. The target was the supermassive black hole at the center of the galaxy M87, approximately 53 million light-years away and containing a mass roughly 6.5 billion times that of the Sun. The image showed a bright ring of superheated gas and plasma swirling around a central darkness, the shadow of the event horizon, the region from which no light escapes. It was blurred, imperfect, assembled from data collected simultaneously across multiple continents and processed over months. And it was extraordinary. Not because it was surprising. The image matched theoretical predictions with remarkable precision, but because it represented something that had seemed, not long before, entirely beyond reach. A glimpse, however imperfect, of one of the most extreme objects the universe contains, obtained not through fiction or inference, but through light. Most of the universe is inaccessible to the unaided eye. The galaxies we study with our most powerful telescopes are invisible without them, faint smudges requiring hours of exposure to reveal their structure, separated from us by distances that make their light almost impossibly faint by the time it arrives. But there is one exception available to almost anyone on any clear and reasonably dark night in the Northern Hemisphere. The Andromeda Galaxy, the nearest large galaxy to our own, containing perhaps 1 trillion stars, lying more than 2.5 million light-years away, is visible without any instrument at all. It appears as a soft, slightly elongated patch of diffuse light, modest and easy to overlook, but unmistakably there once you know where to look. The light reaching your eyes when you find it left Andromeda more than 2.5 million years ago, before our species existed, before the ice ages that shaped the landscape of our world. It has been traveling through the expanding universe ever since, and it ends its journey on the retina of anyone willing to stand outside on a dark night and look. You are looking at an entire galaxy, 100 billion stars, vast clouds of gas and dust, a structure comparable in scale to our own Milky Way, with no more equipment than the eyes you were born with. There are not many moments in astronomy that require so little and offer so much. On the 14th of September 2015, 2 extraordinarily sensitive instruments, one in Louisiana, one in Washington State, registered something that had never been detected before. A gravitational wave, a ripple in the fabric of space-time itself, produced by the collision of 2 black holes more than 1 billion light-years away. The signal lasted less than a second. It arrived at one detector slightly before the other, allowing scientists to determine roughly which direction it had come from. Its precise frequency pattern, a rapid chirp, rising in pitch before abruptly ending, matched exactly what the equations of general relativity predict for 2 black holes spiraling together and merging. The distortion of space-time caused by the wave, by the time it reached Earth, was almost incomprehensibly small. It stretched and compressed the 4-kilometer arms of each detector by a distance thousands of times smaller than the width of a single proton. Detecting it required instruments of almost absurd precision, decades of technological development, and the careful elimination of every other possible source of vibration. And yet it was detected. Einstein had predicted gravitational waves a century earlier, in 1916, and had privately doubted they would ever be measurable. He was wrong. On a quiet autumn morning, a tiny detector on a small planet registered the echo of a collision between 2 invisible giants, an event that had occurred 1 billion years ago in a galaxy we will never visit, producing a wave that crossed the universe to tap, almost imperceptibly, on the instruments we had built to listen. Most of the black holes we know about formed from stars. A massive star exhausts its nuclear fuel, its core collapses under gravity, and if the conditions are right, a black hole is born, a remnant of the stellar life that preceded it, carrying the mass of its progenitor compressed into a region of space from which nothing can escape. But there is another possibility. Black holes that formed before any star existed. In the first fractions of a second after the Big Bang, the universe was unimaginably hot and dense, and the distribution of that density was not perfectly smooth. Some regions were fractionally denser than others, tiny fluctuations in the otherwise uniform plasma. In places where those fluctuations were large enough, gravity may have been sufficient to collapse the local matter directly into a black hole, without any intervening stellar evolution. These are called primordial black holes. We have not yet directly detected any, and their existence remains hypothetical. But they are consistent with the physics of the early universe, and they carry potentially profound implications. Some might be very small, the mass of an asteroid compressed into a space smaller than an atom. Others might have grown over cosmic time. If they exist, they would be the oldest objects in the universe. Not remnants of stars, not products of cosmic evolution, but fossils of the first seconds of time, dark and silent, still drifting through the present universe with no trace of what they are. Quantum entanglement is one of the most counterintuitive phenomena in all of physics. When two particles interact in the right way, they can become entangled. Their quantum states linked in such a way that measuring one instantly determines something about the other, regardless of how far apart they are. There is no signal exchanged, no hidden connection traveling between them. The correlation simply exists, written into the quantum state of both particles simultaneously, in a way that has no classical analog and no intuitive explanation. Einstein famously disliked this feature of quantum mechanics, calling it spooky action at a distance. But decades of experiments have confirmed it beyond any serious doubt. Now consider the scale of the universe. Particles have been interacting and entangling since the Big Bang, across the entire history of the cosmos. Some pairs of particles that were entangled in the early universe may still carry that correlation today, separated by billions of light-years of expansion, each drifting through a different region of the observable universe, and yet, in some quantum sense, still paired. Some physicists have proposed that entanglement may play a deeper role than we currently understand, possibly connected to the structure of space-time itself, perhaps even contributing to the way space holds together at the quantum level. If so, the universe may be threaded throughout with invisible connections. Quantum echoes of ancient interactions, linking its most distant parts in ways that no telescope can observe and no map can show. Black holes are defined above almost everything else by their darkness. They are regions of space-time from which nothing, not matter, not radiation, not light itself, can escape once it has crossed the event horizon. They consume. They retain. They do not give back. And yet, according to a theoretical result derived by the physicist Stephen Hawking in the 1970s, black holes are not entirely silent. They glow. Imperceptibly, vanishingly faintly, but they glow. The mechanism arises from quantum effects near the event horizon. In the restless quantum vacuum, pairs of particles and antiparticles spontaneously appear throughout space. Under normal circumstances, they annihilate almost immediately. But near the event horizon of a black hole, the geometry of space-time can intervene. One particle falls inward, while the other escapes outward, carrying a small amount of energy away from the black hole. Over time, this process, called Hawking radiation, causes the black hole to lose mass infinitesimally slowly. For a black hole of stellar mass, the timescale for complete evaporation through this process exceeds the current age of the universe by an almost incomprehensible factor. A black hole with the mass of the Sun would take longer than 10 to the power of 67 years to evaporate completely. But the process is real, and it ends only one way. Given enough time, more time than the universe has yet existed, multiplied by itself many times over, even a black hole will fade. Not with a collapse, not with an explosion. Just a slow, patient diminishment into nothing. When we learn about the states of matter, we are taught three: solid, liquid, and gas. These are the forms we encounter in daily life, and they cover the range of experience available on the surface of a planet like ours. But they account for a vanishingly small fraction of the matter in the universe. The most common state of visible matter in the cosmos is plasma. a high-energy state in which electrons are stripped away from atomic nuclei, leaving a fluid of charged particles that responds to magnetic fields, conducts electricity across enormous distances, and behaves in ways that have no parallel in the cooler states of matter we usually consider. Plasma fills the interiors of stars. It streams outward from them in stellar winds. It occupies the vast regions of hot gas found between galaxies in clusters. It pervades the intergalactic medium in diffuse, nearly invisible tendrils. Wherever temperatures are high enough or radiation intense enough to ionize atoms, plasma is what results. On Earth, we encounter it rarely and briefly, in lightning, in certain kinds of flame, in the glowing gas of neon lights, in the aurora. These are glimpses of the universe's most common material state, appearing momentarily in the thin, cool envelope of a planet that sits at an unusual extreme of coldness and complexity. The universe in its ordinary condition is not solid ground and liquid water and breathable air. It is plasma, vast, hot, charged, and luminous. For most of human history, our knowledge of the universe came through light. Visible light first, then radio waves, then infrared, ultraviolet, X-ray, and gamma-ray astronomy. Each new window onto the electromagnetic spectrum, revealing aspects of the cosmos invisible to all the others. But they were all, fundamentally, the same kind of information. Variations in the electromagnetic field, traveling at the speed of light. Gravitational waves are something different. They are not electromagnetic at all. They are distortions in the fabric of space-time itself, ripples produced when massive objects accelerate, propagating outward through the universe at the speed of light, passing through everything without being absorbed or deflected. They carry information that light cannot carry. They can emerge from regions of space where light is trapped, from inside collapsing stars, from the final moments before two black holes merge, from the earliest instants after the Big Bang, when the universe was opaque to all electromagnetic radiation. When a gravitational wave passes through a region of space, it stretches distances in one direction while simultaneously compressing them in the perpendicular direction, then reverses, a rhythmic transverse oscillation of space-time geometry itself. The effect is real, but the scale is almost beyond imagining. A wave produced by two colliding black holes, after traveling more than 1 billion light-years, might stretch the 4-kilometer arm of a detector by a distance 20 times smaller than the diameter of a proton. That we can detect such things at all is one of the quieter triumphs of human curiosity. Every telescope is a time machine. Because light travels at a finite speed, every image we capture of a distant object shows that object not as it is now, but as it was when the light we are seeing left it. For objects nearby, the delay is negligible. For the most distant objects the James Webb Space Telescope can observe, it amounts to billions of years. This means that some of the galaxies appearing in Webb's deepest images no longer exist in the form we are seeing them. They may have merged with neighboring galaxies, their spiral arms dissolved into the more uniform structure of an elliptical system. They may have been disrupted, stripped, or transformed beyond recognition by the gravitational interactions of billions of years. The galaxy we observe is a snapshot, a frozen moment in a story that has continued long since. The light captured in that image left its source when the universe was young, traveled across expanding space for billions of years, and finally arrived at a mirror in space that was not built until the universe was already most of the way through its present age. What Webb shows us in its deepest fields is not the universe as it is. It is the universe as it was, at dozens of different moments simultaneously, each distance corresponding to a different era, a different chapter in the long history of cosmic structure. A telescope pointed outward is also pointed backward, always. Our planet is approximately 4.5 billion years old. By cosmic standards, that is a significant stretch of time, long enough for continents to form and erode, for life to emerge and diversify, for a lineage of organisms to slowly develop the capacity for curiosity about the universe they inhabit. And yet when we observe galaxies at distances of 8 or 10 billion light-years, We are receiving light that left its source before any of that happened. Before the sun ignited, before the disk of gas and dust from which our solar system would eventually condense had begun to gather, before Earth existed in any form. That light has been traveling through the expanding universe for longer than our planet has existed. It has crossed distances that were themselves growing as it traveled, arriving redshifted and stretched, softened by the journey into longer wavelengths than those in which it departed. When it finally reaches a telescope, or the retina of an eye on a clear night for the nearest examples, it completes a journey that began in a universe that did not yet contain us. The stars whose light we see in those distant galaxies may be long dead. The galaxies themselves may have transformed beyond recognition. But the light persists, carrying its ancient information patiently across the dark, arriving at last at a world that was not yet born when it began. The universe is not always visible to those who look. Between the stars, filling the arms of galaxies and the molecular clouds where new stars form, drifts a fine, pervasive material, interstellar dust. Not the household variety, but microscopic grains of carbon and silicate compounds, each smaller than a bacterium, collectively capable of blocking enormous quantities of light. When a galaxy lies behind a sufficiently dense dust cloud, its visible light may be almost entirely absorbed before reaching us. The galaxy is there, massive, containing billions of stars, occupying a real volume of space, but to an optical telescope, it is simply absent. The sky in that direction appears empty. This effect is most pronounced along the plane of our own galaxy, where dust is thickest. This region of sky, called the zone of avoidance, conceals an unknown number of galaxies behind the obscuring material of the Milky Way's disk. Astronomers have used infrared and radio observations, wavelengths that pass through dust more freely than visible light, to find galaxies hiding in these regions, some of them substantial systems that would otherwise have been catalogued long ago. In some directions, entire galaxy clusters lurk behind the dust, their presence inferred from the gravitational influence they exert on their surroundings, seen only when viewed through wavelengths that the dust cannot easily stop. Darkness does not always mean absence. Sometimes it means the wrong kind of light. The observable universe has a boundary. Beyond a certain distance, roughly 46 billion light-years in every direction, light has not had sufficient time to reach us, and we cannot observe what lies further out. This limit is real, and it is not something we can overcome regardless of how powerful our instruments become. But the observable universe is not the universe. It is simply the portion of the universe that is available to us. A sphere of accessibility defined not by any physical boundary, but by the finite speed of light and the finite age of the cosmos. Beyond that sphere, space almost certainly continues. Current measurements of the geometry of the universe suggest that it is either infinite in extent, or so close to flat that any curvature would only become apparent on scales far larger than what we can observe. In either case, the universe extends far beyond what we can see. If it is truly infinite, the implications are difficult to absorb. An infinite universe contains infinite matter, infinite space, infinite time ahead of it. Every configuration of matter that is physically possible would, in an infinite universe, occur, not once, but infinitely many times. We cannot confirm this. We cannot rule it out. The honest answer is that we do not know how large the universe is, and we may never know. What we do know is that the edge of what we can see is very likely not the edge of what exists. The universe does not require our observation to continue. Every second of every day, high-energy particles rain down on Earth from space. They arrive from every direction, at all hours, in all weather. Most are deflected by the planet's magnetic field, or absorbed high in the atmosphere before they can reach the surface. But some make it through, and a small number pass through everything, buildings, ground, and living tissue, without pause. These are cosmic rays. Despite the name, they are not rays in the electromagnetic sense, but particles, mostly protons and atomic nuclei, along with some electrons and other fragments, accelerated to extraordinary speeds by some of the most energetic processes in the universe. Supernova explosions, pulsars, the jets of active galactic nuclei, and perhaps the vicinity of black holes all contribute to their production. The most energetic cosmic rays carry kinetic energies that dwarf anything produced by the most powerful particle accelerators on Earth. Their origins remain partially mysterious. For the highest energy particles, the precise sources have not been definitively identified. When a high-energy cosmic ray strikes the upper atmosphere, it produces a cascade of secondary particles, a shower that spreads downward through the air, detectable by instruments on the ground or in aircraft. These showers can span kilometers. Each one began perhaps in the death of a star, or at the edge of a black hole, or in a process we have not yet fully understood. A particle accelerated across thousands of light years before finding at the end of its journey a small blue planet in an unremarkable corner of the galaxy. The question feels natural. If the Big Bang was the beginning of the universe, what came before it? What existed in the moment before the explosion? What occupied the space into which the universe expanded? But the question may contain a false assumption. According to general relativity and the cosmological models built upon it, time itself is not a pre-existing container into which the universe was placed. Time is part of the universe, a dimension of space-time, woven together with the three spatial dimensions we move through, governed by the same physics that governs everything else. If space-time itself began at the Big Bang, then the concept of before has no referent. There was no time in which a before could exist. Asking what came before the Big Bang is, in this view, similar to asking what lies north of the North Pole. The question is grammatically correct, but it asks about a direction that does not exist from that location. Some theories propose different answers, quantum cosmological models in which the universe emerged from a timeless quantum state, or cyclic models in which a previous universe preceded our own, or multiverse frameworks in which our Big Bang was one event among many in a larger structure. Each carries its own difficulties and uncertainties. What all of them share is a recognition that time, as we experience it, is not guaranteed to extend backward without limit. The beginning of the universe may also have been the beginning of the very thing that makes beginnings possible. When the first catalogues of unusual radio sources were compiled in the mid-20th century, the objects associated with some of the strongest signals appeared, in visible light as nothing more than faint points, indistinguishable from ordinary stars. They were given a name reflecting this appearance, quasi-stellar objects, shortened to quasars. But their spectra were wrong. The lines produced by known elements appeared at positions so far shifted from their expected wavelengths that astronomers initially struggled to identify them. When the redshifts were finally correctly interpreted, the implication was staggering. These objects were not nearby stars. They were not even within our galaxy. They were among the most distant objects in the observable universe, located billions of light years away, and yet bright enough to be detected across those distances. To be visible at all from such distances, they had to be producing energy at a rate that dwarfed entire galaxies. The explanation, arrived at gradually over subsequent decades, is that a quasar is the intensely luminous core of a distant galaxy, powered by a supermassive black hole actively consuming surrounding material. As gas spirals inward, it heats to extreme temperatures and radiates across the full electromagnetic spectrum with an output that can exceed the combined light of hundreds of billions of stars. They looked like stars. They were, in reality, the brightest sustained light sources the universe produces, beacons blazing from the universe's early epochs, so distant that the light arriving now left its source before our solar system existed. The Milky Way does not drift through space freely, subject only to the random motions accumulated over its long history. It is being pulled. The entire local group, the Milky Way, Andromeda, and the dozens of smaller galaxies gravitationally bound to them, is moving in a specific direction, drawn by concentrations of mass on scales far larger than any individual galaxy. The primary attractor lies in the direction of the constellation Centaurus, roughly 250 million light-years away. This region, known as the Great Attractor, contains a massive accumulation of galaxy clusters whose combined gravitational influence reaches across hundreds of millions of light-years. For decades, it was difficult to study directly because it lies along the plane of the Milky Way, partly hidden behind the dust and stars of our own galaxy. Beyond even the Great Attractor lies the Shapley supercluster, one of the most massive concentrations of matter in the observable universe, located some 650 million light-years away, contributing its own gravitational pull to the motion of our local region. We are not stationary. We are not simply orbiting the galactic center and leaving it at that. We are part of a vast, slow gravitational current, a river of galaxies moving together across scales that take hundreds of millions of light-years to describe, drawn towards structures whose full extent we are still in the process of mapping. The destination, such as it is, remains partially hidden. But the motion toward it is real, measurable, and has been accumulating for billions of years. The universe has not always contained stars. For the first few 100 million years after the Big Bang, the cosmos was dark, hydrogen and helium gas filling space without any source of light, no fusion yet underway, no photons being produced by nuclear fires. The darkness was not empty, but it was complete. Then the first stars ignited and the universe entered a new era. Over the following billions of years, star formation spread through galaxy after galaxy, building up across the cosmos, reaching a peak somewhere around 10 billion years ago when new stars were forming at a rate perhaps 10 times higher than today. Since that peak, the rate has been declining. The supply of cold gas available to form new stars is gradually being depleted, locked up in existing stars, blown outward by supernova winds, or heated to temperatures at which it cannot easily collapse under gravity. The universe is not yet dark again, but the golden age of star formation is already behind us. We live in what might be thought of as the long afternoon of the stellar era, past the peak but still surrounded by enough active star formation that the night sky remains filled with light. New stars are still being born. The Milky Way still forms several new stars each year. The season has not ended, but it is turning. The universe that blazed with star formation at its most productive is moving, slowly and irreversibly, toward a quieter time. What we see tonight, looking up, is a sky that will not always look this way. Star formation is not an eternal process. It depends on a specific set of conditions: cold, dense clouds of gas, rich in hydrogen, able to collapse under gravity when the conditions are right. These clouds exist now, and they have existed throughout most of cosmic history. But they will not always be there. Over time, the raw material for new stars is consumed. Existing stars lock hydrogen away in their interiors, fusing it into heavier elements. When they die, some of that material is returned to space through supernova explosions and stellar winds. But some is retained in stellar remnants, white dwarfs, neutron stars, black holes, and removed from the cycle permanently. Meanwhile, the expanding universe gradually separates galaxy clusters from one another, preventing the large-scale infall of fresh gas that might otherwise replenish star-forming regions. Within individual galaxies, feedback from active black holes and intense stellar winds can heat the remaining gas to temperatures at which it can no longer collapse. Gradually, over billions of years, the supply runs low. The most massive stars, the blue giants that burn so brightly, will be first to go. Then stars like our Sun. Then the smaller, dimmer red dwarfs, which burn their fuel so frugally that some will last for trillions of years. But eventually, the last star will form. It will be a small, cool, unhurried red dwarf, and it will burn for an extraordinarily long time before it too fades. After it, no more will follow. The universe will not end then, but it will begin, very slowly, to go dark. Everything we have ever observed with any instrument, every star, every galaxy, every nebula, every planet, every atom of gas drifting through intergalactic space, accounts for only a small fraction of the matter in the universe. Approximately 15%. The remaining 85% is something we have never directly detected, something that emits no light, absorbs no light, and interacts with ordinary matter only through gravity. We call it dark matter, for want of a better name. The name describes only what it is not visible, not electromagnetic, not anything we have a direct handle on. What it actually is remains one of the most significant open questions in physics. Its existence is not seriously in doubt. The evidence for it is extensive and comes from multiple independent directions. Galaxies rotate in ways that cannot be explained by the gravity of their visible mass alone. Galaxy clusters bend light from objects behind them more strongly than their luminous matter would suggest. The large-scale structure of the cosmic web, with its specific pattern of filaments and voids, matches the predictions of models that include dark matter and does not match models that leave it out. Something is there. It holds galaxies together, guides the formation of cosmic structure, and constitutes the majority of all the matter that exists. We move through it constantly as it moves through us, a vast invisible framework on which the visible universe is draped like light on a structure we cannot see. The first galaxies formed when the universe was still young, a few 100 million years after the Big Bang, when the first stars had recently ignited and the cosmos was still assembling its large-scale structures from the primordial gas. The light those galaxies produced was the light of hot, young, massive stars, blue and ultraviolet, brilliant and short-lived. That light has been traveling ever since. And as it traveled, the universe expanded around it. The expansion of space does not simply carry light along, it stretches it. Each wavelength is pulled longer by the growth of the space through which it moves, shifting the light progressively toward the red end of the spectrum and eventually beyond it into the infrared. By the time light from the earliest galaxies reaches us today, after a journey of more than 13 billion years through an expanding universe, it has been stretched so thoroughly that it arrives not as visible light at all, but as infrared radiation, long wavelength warmth, invisible to human eyes, detectable only by instruments cooled to very low temperatures to prevent their own heat from drowning out the signal. This is why the James Webb Space Telescope was designed around infrared detection. The ancient light it seeks has been shifted far beyond what ordinary optical telescopes can see. Webb chases the stretched remnants of the first starlight, signals that began as the fierce blue glow of massive young stars and arrive billions of years later as a whisper of gentle warmth. The holographic principle is not a metaphor. It is a serious proposal arising from rigorous mathematical work in theoretical physics, suggesting that the information content of a region of space may be entirely encoded on its boundary, the surface surrounding that volume, rather than distributed throughout the volume itself. The idea emerged from studies of black holes, where a deep puzzle arose. What happens to information that falls past the event horizon? The mathematics suggested that the information is somehow preserved on the two-dimensional surface of the horizon, rather than being lost inside the three-dimensional volume of the black hole. Some physicists have extended this reasoning to the universe as a whole. In this view, everything we experience as three-dimensional, depth, volume, the apparent solidity of matter occupying space, might be a kind of projection arising from processes encoded on a distant two-dimensional boundary of the universe. This does not mean the world is not real, or that our experience of it is illusory in any everyday sense. The physics of the projected reality is entirely self-consistent. But it does suggest that the way we intuitively think about space, as a genuine three-dimensional container holding things at real depths and distances, may not capture what is actually fundamental. The universe we inhabit may be, in some precise mathematical sense, a representation of something that exists in fewer dimensions than we perceive. Reality is real, but its deepest structure may be stranger than its surface suggests. To every sense we possess, and to every instrument we have built, space appears smooth. A continuous, seamless medium extending in 3 dimensions, divisible without limit, offering no resistance to subdivision and no fundamental unit of length, below which the concept of distance loses meaning. But some approaches to quantum gravity, the as-yet incomplete project of reconciling quantum mechanics with general relativity, suggest that this apparent smoothness may be an illusion, valid only above a certain scale. Below the Planck length, approximately 10 to the power of -35 meters, a distance so small that no physical process we know of could probe it directly, space may cease to be continuous. It may instead be composed of discrete units, a kind of granularity in the geometry of the universe below which the ordinary concepts of distance and direction simply do not apply. At this scale, space-time may take on a foamy, fluctuating texture, a seething structure of quantum geometry in which the smooth fabric of relativity dissolves into something more fundamental and less familiar. We cannot test this directly. The Planck scale is many orders of magnitude beyond the reach of any conceivable instrument. But the mathematical frameworks that point toward it, loop quantum gravity, string theory in some formulations, and others, take it seriously as a feature of reality. Everything we know, everything that exists, may rest on a foundation that is not smooth at all. A universe with texture at its very bottom, granular, discrete, and irreducibly strange. Our sun rotates once approximately every 25 days at its equator, a stately pace that causes no particular structural difficulties for a star of its size and composition. Some larger stars rotate faster. But among the fastest rotating objects in the universe are a category of stellar remnants so extreme that their rotation rates seem almost incompatible with the solidity of matter. Millisecond pulsars are neutron stars, the dense remnants of collapsed massive stars, roughly 20 kilometers across, but containing more mass than the Sun, that rotate hundreds of times per second. Some complete more than 700 full rotations every second. At the equator of such an object, the surface moves at an appreciable fraction of the speed of light. The entire star, a city-sized sphere of nuclear density matter, completes a full rotation in less than 0.002 of a second. These objects reached their extraordinary spin rates through a process of gradual acceleration. In binary systems, a neutron star can draw matter from a companion star over millions of years, and each infalling particle carries angular momentum that adds incrementally to the neutron star's rotation, spinning it up over cosmic time. As they rotate, they sweep beams of radiation across the sky, detectable on Earth as pulses arriving with a regularity that rivals the best atomic clocks. They are among the most precisely timed objects in the universe, spinning in the dark with a consistency that allows their pulses to be predicted years in advance. The fate of the universe is not written in fire or ice, in dramatic collapse or sudden cessation. The evidence we have, an expanding universe, with that expansion accelerating, points towards something far slower and far quieter. As dark energy continues to drive galaxies apart, the universe will become progressively more isolated. Galaxy clusters will remain gravitationally bound to themselves, but the spaces between clusters will grow until no light from one can reach another. Each bound group of galaxies will become an island, surrounded by an expanding darkness containing nothing visible. Within those islands, star formation will slow and eventually stop as the cold gas runs out. Existing stars will burn through their fuel on timescales ranging from millions to trillions of years, fading one by one from blue to yellow to red to nothing. The most long-lived red dwarfs will be the last to go. After the stars, the remnants persist, white dwarfs cooling imperceptibly, neutron stars spinning down, black holes slowly evaporating through Hawking radiation over timescales so vast they resist intuitive comprehension. Protons themselves may eventually decay, dissolving ordinary matter into radiation over timescales longer than the current age of the universe, raised to enormous powers. At the end, if an end can be spoken of, there is no explosion, no dramatic finale. There is simply a universe that has grown cold and still and dark, energy spread so thinly across such vast distances that nothing further can happen, ever. Not a conclusion so much as a cessation. A universe that has simply finished. In the hearts of some galaxies, Conditions exist that generate outflows unlike anything produced by ordinary stellar processes. Where star formation proceeds at extreme rates, or where a supermassive black hole is actively consuming surrounding material, the combined energy output can drive powerful winds outward from the galactic center, carrying gas, dust, and even newly formed stars far beyond the galaxy's visible boundary. These galactic superwinds can move at thousands of kilometers per second. They can stretch for tens of thousands of light-years, pushing material out of the galaxy's disk and into the surrounding intergalactic medium. In doing so, they strip away the cold gas that would otherwise continue forming stars, effectively shutting down the galaxy's star formation on timescales of hundreds of millions of years. But the consequences are not entirely destructive. The material blown outward carries with it the heavy elements forged in stellar interiors and distributed by supernova explosions: carbon, oxygen, iron, and the rest of the periodic table's lower entries. These elements are spread into the space between galaxies, where they may later be incorporated into new generations of stars and planets in other systems. A galaxy breathing outward, exhaling the products of its own stellar life into the surrounding cosmos, impoverishing itself in the short term, but seeding the larger universe with the chemistry that future complexity will require. Even depletion on cosmic scales can be a form of generosity. The universe is not uniformly filled with matter. On the largest scales, it is structured into a web of filaments and clusters, surrounding vast regions of relative emptiness, cosmic voids, where the density of matter is significantly below the universal average. These voids are not empty in any absolute sense, but they contain far fewer galaxies, far less gas, and far less dark matter than the surrounding structure. Some researchers have proposed that our own solar system, our galaxy, and our entire local region of the universe may sit within one of these underdense regions. Not at the heart of a dense cluster, not along a prominent filament, but inside a void, a quieter, more sparsely populated corner of the cosmic web. If true, this would have observable consequences. Light traveling toward us from outside the void would be affected by the transition from underdense to average density space. The apparent rate of cosmic expansion, as measured locally, might differ slightly from the true global average, because we would be sampling the universe from an atypical location. Some astronomers have proposed that living inside a void could help explain certain tensions in cosmological measurements, discrepancies between different methods of measuring the expansion rate of the universe that have persisted stubbornly despite considerable effort to resolve them. We cannot step outside our region of space to verify its density from a neutral vantage point, but the possibility remains. We may inhabit not the typical interior of the cosmic web, but one of its quieter, emptier chambers, drifting through a vast, gentle underdensity, surrounded by a universe that is, on average, busier than the space immediately around us. A neutron star is already one of the most extreme objects in the universe, a stellar remnant compressed to nuclear density, spinning rapidly, radiating energy across the electromagnetic spectrum. But within the population of neutron stars, there exists a subset whose properties push even further into territory that strains description. These are magnetars, and what distinguishes them is their magnetic fields. The magnetic field at Earth's surface is strong enough to deflect a compass needle, to guide migrating birds, to protect the atmosphere from the solar wind. A typical neutron star's magnetic field is already 1 trillion times stronger than this. A magnetar's field is stronger still, perhaps 1,000 times more intense than an ordinary neutron star, and so far beyond anything producible in a laboratory that the comparison becomes almost meaningless. At these field strengths, the vacuum itself behaves differently. The ordinary rules governing how light travels through empty space break down. Atoms are distorted into elongated shapes aligned along the field lines. The surface of the magnetar is locked into a rigid crystalline crust by magnetic forces. Periodically, as the magnetic field shifts and the crust adjusts, a magnetar releases a burst of energy, a flare of X-rays and gamma rays that can, for a fraction of a second, outshine the entire galaxy. One such flare, originating from a magnetar on the far side of the Milky Way, was intense enough to partially ionize Earth's upper atmosphere from a distance of 50,000 light-years. These are not hypothetical extremes. They are measured, documented, and in some cases have made themselves known to instruments on our own planet. The universe, on its largest scales, is supposed to be smooth. Not uniform in detail, galaxies cluster, filaments form, voids open up between them, but statistically homogeneous when averaged across sufficiently large volumes. This principle, called the cosmological principle, underlies virtually all of modern cosmology. It is the assumption that no region of the universe is fundamentally different from any other, that there are no structures so large they violate the overall uniformity of the cosmic distribution of matter. In 2013, astronomers identified a structure that challenges this assumption. The Huge Large Quasar Group is an assemblage of quasars, the brilliantly luminous cores of ancient active galaxies stretching across approximately 4 billion light-years of space. It contains roughly 73 quasars, connected across a region so vast that light traveling at the maximum speed the universe allows would take 4 billion years to cross it. Current theoretical models suggest that structures larger than approximately 1.2 billion light-years should not exist, that the universe's large-scale homogeneity prevents the formation of coherent structures beyond that scale. The Huge Large Quasar Group exceeds that limit by a considerable margin. Whether it constitutes a genuinely gravitationally bound structure or a statistical concentration that appears connected by chance remains debated. But its existence, documented, measured, and confirmed, raises quiet questions about whether the cosmological principle holds as completely as we have assumed, and whether the early universe formed patterns of organization larger and more intricate than our models predict. Gold is rare. Not merely in economic terms, not just scarce relative to demand, but genuinely rare in the universe. The reason for this rarity is written into the physics of how heavy elements are made. The lightest elements, hydrogen, helium, and a small amount of lithium, were forged in the Big Bang itself, in the first minutes of the universe's existence. Heavier elements, up to iron, are produced in the cores of stars through nuclear fusion, the same process that generates the energy making stars shine. Iron represents a kind of limit. Fusing elements heavier than iron consumes energy rather than releasing it, and ordinary stellar fusion stops there. To create elements heavier than iron, gold, platinum, uranium, and the rest of the heavy end of the periodic table requires something more extreme. The leading mechanism is the rapid neutron capture process, which occurs in environments of extraordinary neutron density and temperature. Two such environments are known: the collapse of certain massive stars in supernova explosions and the collision and merger of two neutron stars. When neutron stars collide, they produce a gravitational wave signal detectable across billions of light-years. And they also synthesize, in the brief violence of the merger, quantities of heavy elements, including gold, that are then flung outward into space. Over cosmic time, this gold mixes into gas clouds, condenses into new stars and their planetary systems, and eventually, in rare cases, finds its way onto the surface of a small rocky planet. Every atom of gold that has ever existed was made in catastrophe. The ring on a finger, the circuitry in an instrument, the flecks recovered from a riverbed, all of it arrived here via the collision of two of the densest objects the universe produces. Before the universe was 380,000 years old, matter and radiation were locked together in a hot, dense plasma. In that plasma, two forces competed continuously: gravity pulling matter inward toward regions of higher density and radiation pressure pushing outward against the compression. The result of this competition was oscillation, pressure waves rippling through the plasma, alternately compressing and rarefying the gas across enormous scales. These were, in a meaningful physical sense, sound waves. Acoustic oscillations propagating through the early universe at roughly half the speed of light, carrying energy and imprinting patterns of density variation into the cosmic plasma. When the universe cooled enough for neutral atoms to form and radiation to decouple from matter, those oscillations stopped. The plasma froze. The sound waves that had been traveling through it could travel no further, and their pattern was preserved, fixed into the distribution of matter at the moment the universe became transparent. Today, billions of years later, that frozen pattern is still visible. It appears as a preferred separation distance between pairs of galaxies, a subtle statistical excess at a specific scale, determined by how far a sound wave could travel in the early universe before the plasma froze. This feature, known as the Baryon Acoustic Oscillation Scale, provides a standard ruler that cosmologists use to measure the expansion of the universe across cosmic time. A sound that rang through the early cosmos for hundreds of thousands of years, then stopped and left its final position written into the large-scale structure of everything that followed. A frozen echo, still readable in the sky. In the long history of the universe, galaxies have rarely existed in true isolation.